Test. Perfect. So, hello everyone. We are Filip and Toufic. We are working at SpaceComputer, and we have prepared for you a great workshop regarding what we want to do and what are some of the challenges we are facing with respect to building solutions in space. And our talk of the title is From Stars to Bits, Space Infrastructure for Safe Computation. So I believe some of you might have already heard in the recent weeks, months about the hype regarding space data centers. And as we can see more and more, it's not only becoming a hype, but it's actually becoming a reality. We have many companies working on it. We have Google looking into the solutions, SpaceX, of course, but also recent startup from YC called StarCloud that is like really actively pushing on narrative. And just a few days ago, they raised a huge Series A of over 170 million to actually find a way on how to make efficiency of space data centers comparable to the one on Earth. So overall, we see that the tendency is clear. More compute will be shifting to space. What does it mean for us? Space is open for business more than ever before. And the main unlocking capabilities is, to be fair, due to SpaceX, where we see that the launching of any type of gear to space is becoming way cheaper over the years, where it started in the order of like tens of thousands of dollars per kilogram. Now with Falcon 9, it's in the order of like thousands of dollars. And with Starship, that should be available in the next years, we are talking about hundreds or even tens of dollars per kilogram, which unlocks many new use cases that were not really thought of before. So what does it mean for us as a solution we want to build? We definitely envision that there will be a need for a lot of security in this context because space itself plays an important role in many activities regarding communication and other, depending on who is the customer, of course. And we have to focus on providing communication with respect to edge computing and security on that side. You have to focus on in case you actually want to execute any type of sensitive workload on the satellite in space. Either it's AI that we see currently is like the driving force for many aspects to storing keys and providing secure capabilities for your systems in space. You need to also have a way on how to ensure it. And lastly, since you will have more compute in space, you can also start to think about space-native applications that will be fully developed for solutions in space. And the question is, what is the state of space as of now? We see that definitely there is a huge potential for the next 10 years with respect to Starlink being available on most of the satellites and many others. But as of now, we are not there yet. We can see that actually many of the issues that we are facing on Earth or we have faced on Earth maybe 20, 30 years ago is actually still dominant with respect to space technologies. We see a lot of challenges with respect to just even being able to communicate with your infrastructure, unless you are using, for example, solutions like a Starlink, which is still not widely adopted beyond SpaceX solutions. And this is also proven by recent studies where, for example, recent research has shown that around 50% of satellite traffic is still unencrypted, especially if you consider that in the past, only state-level actors were actually able to go and, for example, listen to their traffic. Nowadays, it's becoming a commodity. If you just buy any type of cheap software-defined radio, anyone can actually go and listen to traffic that is being sent and broadcasted to Earth. So we definitely see a huge shift, and we have to start to also adjust our architectures accordingly with that. So our general idea is to crawl before you walk and walk before you run. So this is something we try to follow, and actually we have seen over the past roughly 18 months when we started to build SpaceComputer, there are actually many fundamental challenges we have to solve before we can actually reach the reality of large-scale systems that can run in space. And how we envision ourselves, we want to be providing a security layer where we can have and rely on other third-party constellations, but also use our own satellites that will be equipped with unique type of capabilities. And users on Earth will be able to consume it, but of course we also envision in the future that other satellites themselves will be able to use our capabilities. Well, this is quite a unique, especially from a security perspective, but it's also a pain from engineering perspective because we have to design for this stuff in mind with respect to physical isolation. Because once you send stuff, it's a little bit hard to maintain it, but also it provides very much superior security guarantees because the infrastructure operates beyond borders, beyond reach, and it's definitely immune to physical tampering once it's up in the space. And this is definitely providing very interesting capabilities, especially for those that might be familiar with some of the concepts of security. If you can't reach it, it definitely makes your attack vector quite more challenging with respect to physical access. And this is kind of when we dive into the aspects of how do we envision the infrastructure to be usable for safe computation. So we see that, of course, the users on Earth should have a seamless experience as they are used to for interacting with AWS or other solutions. As of now, it's very far from that, but it's basically where we come as a company to provide a solution. We are designing our secure gateway called orbitport that aims to provide the interface between the users on Earth, expose the services to them, but also provide the abstraction to the users so they can easily communicate with what is happening in space, either with other satellites, with our own satellites, or, as we will introduce later on, SpaceFabric equipped satellites. And orbitport itself will be managing the interface between different type of ground station providers. As a fun note, you read it right, these are actually really mailboxes. As of now, if you want to talk with some of your infrastructure in space, you really have to rely on sending your messages to a ground station provider via email that will eventually forward it to space. And depending on the ground station provider, some are a bit more sophisticated with an API, some are not there yet. This is basically also one of the pain points we want to solve with orbitport. We want to unify the interfaces that will be facing to the ground station providers, and you as a user can just like interact via a API that you are comfortable with, and can later on make sure that it will be able to communicate with your infrastructure in space. Kind of unlocking each of the individual items on the figure, so we'll be starting actually what does it mean to run something on our satellites, or what is actually SpaceFabric itself. Maybe quick raise of hands. Who of you have heard of trusted execution environments? Wow, we have a TE crowd here, which is great. So I will just go over it quickly for the people online. General TEs are an isolated region on a CPU that is providing additional instructions to your application that you can later on execute and run. And it promises secure location for your code and data. And in general, depending on the type of a TE, it aims to offer confidentiality and integrity for the data that are running inside of the enclave. And I think most crucial aspects, it's providing remote attestation capabilities, so you can actually convince others with a cryptographic proof that your application is actually running inside of a trusted execution environment itself. For those that already know, there are in general two types of families: process-based families and VM-based solutions. There, as it's kind of from the name clear, we have for the process-based solutions, we in general see that we are just able to run a particular sensitive compute as a part of the process inside of the enclave. And for the VM-based solutions, as it's kind of from the name obvious, we're actually like putting the whole confidential virtual machine. That is something that you can easily run and spin. The main difference is the size of so-called trusted compute base. So of course, if you have the whole virtual machine, this is assumed to be trusted running inside of the TE. It's a bit larger in comparison to the process-based solutions. And also the threat model is slightly different in the context that you assume malicious hypervisor, and actually for the process-based, you can assume malicious host operating system as well. And in recent months and years, we have seen quite a few issues with the TE, especially due to the threat model they have, which basically currently relies on a so-called guy with a Glock who is actually ensuring the physical protection of TEs. And of course, as we have seen in the recent months, there were quite a few attacks exposing actually some of the sensitive key material out of the TE, and even be able to create an attestation that your code is actually running in an authentic information. Which inherently means, which is my other line of work, inherently means that actually you have to trust the operator not to behave maliciously. Which of course is always sparking when there's a new issue with TE. It's always sparking an interesting X wars with respect to posts that TEs are dead and they don't have future. I think it's not about that. I think TEs definitely provide an interesting value, and I think they should be considered as one of the security solutions we have out there in combination with cryptographic-based solution. And for that, we kind of introduced one of our solutions actually aims to solve some of the issues we know with TEs, and this is called SpaceFabric. We just published it last week, and it generally tries to actually think of a future architecture for designing confidential computing in space, and it tries to address some of the challenges we see with TEs on Earth. And I will just provide some of the key contributions in here in high level, and kind of how do we position ourselves. So in the past, there was also the direction about like just space TE, which was the idea of like having a software that is just available on your particular machine with physical isolation. But what we start to see more and more, and this will be definitely a big topic in the space industry, is like you want to not having a dedicated satellite for your particular mission, but you start to be interested in multi-tenancy. What does it mean? That you are not necessarily in the mood to trusting the other people that are sharing the same infrastructure. And for that, we are designing SpaceFabric that is providing quite an interesting set of capabilities. Some of the unique issues that are known in the TE community is that, of course, I didn't dive into it in detail before, as a part of the TE attestation flow, usually the manufacturer itself is injecting itself into the hardware root of trust. TEs in general have the issue that they tell you actually what is the code they are running, but they don't actually tell you anything about where is the code that is running. Of course, the other aspect is the auditability and supply chain. And lastly, especially I think with the announcement of Google, everyone is talking about it quite heavily, had to put it to the slides yesterday, is the post-quantum cryptography transition. It's possible, just like it's something that has to be, I think, more actively discussed as well. And looking at it, we try to look for possible solutions to these problems. So what we identify will be the suitable solution is make sure that the private keys that are used as a part of attestations are never generated on Earth. We are actually relying on two secure elements for our attestation flow. That one of them is open source completely, meaning actually even the hardware design and the firmware is open source. And the second one is established certified solution. And we have identified and designed our own instantiation of so-called proof of execution triangulation. In a short proof of ET, you can ask what came up first, if the ET or the actually words behind it. In this case, we were focusing on actually describing, which is the interesting property, is trying to find a way on how we can actually prove our execution is happening in space. And for that, we have instantiated our protocol that we call Satellite Execution Assurance Protocol. That actually is kind of using the ground stations to issue a form of like a challenge response protocol that will ensure that your satellite is actually really an authentic satellite and it's running in space. And we are in general providing and using the secure approach of making sure the host is secure. We are trying to minimize the TCP. We are finding the aspects of how to offload the sensitive compute to the TE in combination with the HSM that are providing us the key material, and in general try to provide attestations to its user. So we are unfolding all of these aspects in the paper, but the cool part from our side that satellites equipped with our solution will be available later on this year because we have 3 missions plans ahead of us, and the first one will be later on this year in October. So if you're interested to find out more, you can check out the SpaceComputer paper. And with that, we kind of covered what is happening in the space. Now let's dive into actually how do we communicate with it. And this is the part where, again, orbitport comes into the picture. And it aims to provide to the users this trust minimized gateway that is able to communicate. It's providing also the end-to-end confidentiality and integrity. And it in general aims to unlock several of our use cases. One of them will be CTRNG, as we'll be looking into more detailed. And as of now, we are the only party managing it, but actually we'll be partnering with several people to actually run our gateway inside of their infrastructure, inside of TEs as well on Earth. And we in general want to unlock and make this gateway more trust minimized. So one of the solutions is to use TEs on Earth as well, partner with other people, and in general make it open source so actually other people can also go and deploy their instance of orbitport. And in the future, make sure actually that anyone who just wants to interact with the infrastructure can run it on-prem or in different type of settings as well. So on that part, we kind of covered the confidential compute in space. We can now communicate with it. Let's see what are some of the features we can unlock. So one of them is randomness. It's one of the, I would say, funky for us because, of course, you always want to get some radiation from space. And now is the question, how can you actually consume it? Toufic will be diving into the details, actually, what are some of the tricks we do to make sure that the user is confident that our randomness is the related random number that we are consuming. And we already have a couple of recipes you can play with if you're interested. And in general, we are looking also into the aspects of not only public randomness that you can consume as you are used to for NFTs and others, but also find a way on how we can consume private randomness in consensus or other cryptographic protocols themselves. And something that's very exciting for us is key management service, which is a new offering we are currently launching in phase 0 for initial partnership integration. In general, as of now, we are building the solution custom to us because, of course, we have to build for space where we want to run eventually the whole KMS stack. But for now, we are starting to build it on Earth with eventual transition in a hybrid setting between Earth and space, and eventually running it full in space, which will be unlocked by thresholdizing some of the components and using the TEs along the way. So if you are interested, let us know. We also have a portal, basically, as people are used to. If you want to register through OAuth, you can get your respective tokens, and you can start to play around with the infrastructure. Okay, and I think with that we covered most of the aspects of the workflow, and Toufic will now unlock more of the details regarding CTRNG. Thank you.
Great. Thanks, Filip, for giving an overview. So yeah, one of the applications that we have with our space infrastructure is CTRNG. And we were first thinking, where are we talking about randomness? Like usually when we're talking about cryptographic protocol security, we're talking about code, about audit, about monitoring, and we treat randomness as an assumption, but we should not. So randomness is used in a lot of places, in decentralized application, in Web3 mechanisms such as selection, ordering or consensus, and also in core cryptographic protocols. Like if you have any key generation, signature, nonce generation, you need strong randomness. And so the problem that we're trying to solve here is basically making sure that we're having true randomness. We want to make sure that we are generating randomness correctly, that nobody is able to guess it in case that we have real private randomness, that nobody also is able to bias it or influence the random numbers that we're going to get. And also we need to make it verifiable by the user. And we can see that as a randomness supply chain, like we're starting with randomness collection, and at the end, we want to have a randomness that is usable by the user in the application layer. And what we are going to see is all the steps in between so that the user can be confident about it. What are the current existing solutions? For now, we have external solution in which the user that uses the randomness does not generate it itself. And we have here again different subcategories. We have a Hochstein solution. So it's easy for the user to use it, but he has to trust someone else to provide that randomness to it. We have also some on-chain solutions. It's transparent and easier to consume, but it's harder to deliver because there is not really a native randomness on-chain, so you have to trust someone to provide that randomness to you. And how you trust that person, or how do you trust that group of person, and it's also harder to deliver. So this is one group of solution, and the other way, you can just not trust anyone and generate your randomness locally, maybe on your computer or just by an external device. But it's a bit complicated to make it right, and also you are vulnerable to several kind of attacks, like side channel attacks, and your device can be compromised also. So we need a solution for all of this. That keep the source trusted to make sure that you know what's happening, how the randomness is generated, and that randomness should be preserved through transportation. And at the end, you should be able to verify what's happening. And that's the role of our CTRNG, which is cosmic true random number generation. So we're taking randomness from space radiation, which is, as much as we know for now, a non-deterministic process, and use it as a source of randomness. And one of the main benefits of it is like it's outside of reach of any Earth attacker. So any side channel attacks, any compromission is an old threat model. And now the question is, how can we be confident that that randomness is correctly generated and transported? So Filip briefly talked about TEs, and it's one part of the solution. And now let's take a look at other part of the solution. So when we want to verify that randomness is correctly generated, we have two parts of the story. The first part is internal view. Us as a designer at SpaceComputer, we have access to data that public user does not have. We have access to the internal state. We have access to the data that is captured by the sensors, and we have access to the whole system. And in other hand, the user, he only has access to the public information. He has access to the documentation, to open source code, to any attestations that we publish, and of course, he has access to the random number. And it's two different versions that need to be separated separately. So yeah, before diving into the separation, let's just briefly take a look at the type of random number generator. So a TRNG is a true random number generator, and it extracts randomness from a physical source. It's non-deterministic, which is what we want from a randomness source, but it has a lower throughput because each time you want randomness, you have to query that source of randomness. And on the other hand, we have PRNG, which are pseudo-random number generators. And you give it a seed as an input, and you just get as an output a sequence of random number. It's pseudo-random, so it's deterministic, and it's faster, but it's predictable. So if an attacker gets access to the input seed, then he's able to recover the whole sequence of number. And so let's start here with internal verification, how first we make sure as designer to correctly generate that randomness. And for this, we use the NIST SP190 series, which is a certification framework. And it's divided in 3 parts. So NIST A is about how to correctly design a deterministic random bit generator, which is the NIST equivalent of a secure PRNG. On our end, we're not reinventing anything. We will use existing one like CHE20, so I'm not diving into this. NIST B is about the entropy source and the entropy estimation, how we make sure that the sensors in space are providing enough randomness. And NIST C is about combining NIST A and NIST B, the entropy source and the DRBG, to have a full usable RNG. So let's take a look at NIST B and the analysis of the source of entropy. So we first here have the analog noise source, which is our raw space radiation in our end. And we digitalize it and we get some raw data. And this is first the digital noise source. We can apply some conditioning on it. I'll explain in more detail what are the goals of this. And then we need to apply some health stealth also to make sure that it's working correctly. And all of this forms the entropy source, and our goal is to ask how random is our source. But what is it exactly? How random is the source? Let's try to define it. So imagine that I have a source of randomness. For example, I have a source that outputs number between 1 and 10. And you here are an attacker and trying to guess what will be my next output. So if my source is fair, for example, each value is probable at 10%, whatever you will be guessing, you will have a success rate of 10%, which is as good as we want, as much as possible in that case. If our source is biased, for example, 7 appear 50% of the time, if you choose 7, you will have a success rate of 50%. And so you will have a higher rate of guessing, and we can assume that my source is less good than this one. And if my source is broken, then you choose 7 and you have 100% success rate. And so we can try to think about randomness as the more success rate has an attacker on guessing my next number. But you could be telling me, like, for example, if my source is biased and 2 appear 0% of the time, if you choose 2, you will have 0% success rate. And we could conclude that this source is better than this one, even if it's biased. But our goal here is to take your best guess as an attacker so that on our end, we have a lower bound on our entropy estimation, so that we know that we have at least that much entropy in it. And it's a conservative way of thinking about security. And this is just the formalization of this intuition. So we define the entropy as the opposite of the logarithm of Pmax, where Pmax is the best guess of the attacker. And when we apply it to the result before, we just see that the lower is Pmax, we end up with a higher entropy. And the more our source is broken, the less entropies we have, and it makes sense. And so we know how to define entropy. And to define entropy, we need to calculate Pmax. But in practice, Pmax is not that easy to calculate, and we need to estimate it. And for that, we have estimators, and we have a different way to calculate it. And it first depends on the model. If your variable is IID, identically distributed and independent, then you can just count symbol frequencies and then get an estimation of Pmax, depending on what is your frequency in your dataset. But if it's not an ID, you have NIST that provide some other estimators. You have, for example, Markov chain or compression-based estimator. And yeah, so the goal here is to take all that list of estimator. You have around 10, and you calculate, you take the minimum, and that's your lower bound. And to do this on the raw data calculation, you need to take around 1 million data points to collect them before any calculation. So also you need to perform health tests. You need to perform health tests at startup to make sure that each time that you're restarting your source, it started correctly. You need to have also test on demand to make sure that whenever you're having a sensitive operation, you make sure and check that your source is working correctly. And you also make sure, need to have continuous testing to make sure that it's not sliding over time. And for example, some tests, it includes like repetition count test. It detects a long graph of identical value. If you have like a lot of zeros, it should be warning up. And the adaptive proportion test also, it checks how the frequency is evolving over time. If you used to have a certain frequency and now it's changing, you should have an alert. And then once you have your raw output, you may apply conditioning depending on what is your quality on your output, because you still can have some bias or correlation. And for example, if you have an output of 8 bits, maybe inside it you only have 4 bits of entropy. And your goal is to compress it into a cleaner output so that now in 4 bits you have 4 bits of entropies. And you need to understand that this conditioning, it does not create more entropy, and you need to estimate the entropy before applying that conditioning. And then, depending on which conditioning you use, if it's approved by NIST or not, then you're able to claim full entropy or not, saying like, if I provide 8 bits, 100% of that amount is full entropy. So yeah, now let's talk about NIST. So NIST is about the construction of the full random bin generator. And so we've just seen how to estimate entropy on the entropy source. We've not seen, but we will be using a DRBG from NIST-A. And NIST is about combining both. Like you have the entropy source, and you give it as an input to the DRBG. And it explains how to seed and reseed from the source. When it explains also what is the bit limit, because you can't like use one seed and generate random numbers infinitely. It explains what bit limit you should use. And it also explains how to combine multiple sources if you have more than one. And yeah, what we need to understand here is that this NIST certification is a baseline. We should not treat it as a proof that our source is secure, but it's something that's considered good enough to be used in most cryptographic applications. But we still have to keep up with research because yeah, we have a lot of new attacks and things that are discovered. And so here, with our randomness supply chain, so we have some randomness generation here. For example, yeah, space radiation that we discussed. We sample, digitize it, and then we have our raw data collection. And then we can apply the internal verification, us as a team, as we discussed, which is entropy modeling, health test, and then conditioning. And then we will see how it can be usable to the external verification. And so yeah, for recall, external verification, it's for the user point of view. So the user, it sees our product as a black box, and he only has the public information that's available. And his goal is to check as much as possible if the received value looks correct. And we have 2 tools for this. We have statistical verification that I'll explain, and cryptographic mechanisms that Filip talked about it briefly, but I'll re-go on it again. And so the statistical verification, the goal is that the user, he got some random numbers that we provided from SpaceComputer, and he wants to take a look at this random number and say, does it look random? And the goal is to detect bias or correlation, but it only tries to look if it looks random. It cannot prove that it's random. It's only trying to guess if there is things that are obviously broken, but that's the most that it can do. And in practice, we have some statistical test suite like DieHard or DieHarder or NIST, but the most recent one are Test User 1 and Procton, and we'll see how it works. So each test on Test User 1, it computes a statistic on the data and see how much is it surprising. For example, let's say that we have a generator that outputs number between 1 and 10, and let's say we're drawing 1,000 number, and our statistic will be counting how much 7 do we have. We expect to have 107, but we can do more than this. We can say that we have less than 1% chance of filing outside the 75-125 range, and we have around 10% chance of filing outside the 85-115 range. And we can use this to say, for example, if we get like 500 as a count, it's suspicious. It's still possible. If we get it one time, it can still be true. But if we have different tests and we have different very low probability, then we can suggest that our the entropy source is broken. And so yeah, the p-value is what formalizes. It's how surprising is the expected result under our hypothesis. And yeah, if the p-value is too small, we reject our hypothesis. And if it's not too small, then we can just say that we were not able to reject our hypothesis, but we cannot prove anything here. And yeah, so concerning statistical verification, we will very soon release a library on it, which is a Rust library, which includes two of the most recent tests, which is test user 1 and Proctrand. And we have two kinds of bindings here. Rust2C in order to be able to call our code, Rust code to the library, and C2Rust in order to be able to call back the result. And yeah, the goal is that this is open source and pluggable into whatever Rust repository. So you're able to verify with this our source of randomness, but whatever source of randomness in the crypto world, you can verify it with this statistical verification library. And here we just have an example of how it's working. So we took an example with the classic RNG with ecdsa. You define it, you register it, and then depending on which battery test you want to run, for example, if it's small verification you want to do or the big one, you run the corresponding test and you do the verification. And then yeah, this was statistical verification, and now let's look at the other way of verifying things, which is cryptographic verification. And one of the first way we can verify things is by having signatures on the output. If the data is signed, then I know that the data comes from the satellite. So I know where it's coming from, but I just know that it's coming from the satellite. I don't know if it's what generated correctly. And that's the role of TEE attestations, is to make sure that I know that this number was generated on this satellite, and I know it was generated with this code and this process, and it's attested. And another thing is verifiable DRBG output. We can imagine for public beacons that us as SpaceComputer, we can commit to a DRBG seed, and later when we reveal that seed, the user can replay the sequence, verify it himself. And we have also some option to not only commit on a seed and use that seed as the input of the DRBG, but commit on a seed and use the input as a hash of the seed and a public value, for example, a block hash, so that we know that we have not biased the output. So yeah, it all depends on the use case. And here, yeah, we can retake a look at the randomness supply chain to situate things. So one of the things we've talked about is space radiation, but on space we also have TPMs and HSMs that are true source of generation and that have a way to generate random number. So space radiation is one of the sources, but we have two others that are also NIST approved. And so yeah, we've seen how we collect the data, we've seen how we do internal verification, and now we have our input, our output, the user can verify it, and first perform a cryptographic attestation verification, but also perform statistical testing on it. And now he has an input that he can use in whatever he wants, in key generation, in a threshold ecdsa, in leader election. And this is all like private beacon example, but we also can provide public beacon output to make sure that, for example, if we have a lottery or whatever public number that is needed, it can be used also. And so, yeah, we're presenting now a CryptoCity RNG, which is our library that enables you as a user to access the random numbers that we're providing from space. And yeah, it's a Rust library that transports that entropy from our backend to the user. It implements the standard sets so that it's pluggable and can be replaced in any RNG. It has 3 entropy sources. The first one is IPFS beacon, which is 32-byte blocks that comes from the CTRNG backend. This is our main source. Another one is local OS. If you don't trust the randomness for space, or if you want maximum security, you can use your local one in order to get it mixed, so that you have the randomness from space, your local randomness, and you XOR both. You have 3 modes then. You have raw entropy, if you just want the entropy and then plug it into your custom cryptography mechanism. And if you want to have our DRBG on top of it, which is a CHA-20 construction, you can use our, and then you can apply auto-reseed on top of it, which is like every 3,200 bytes or every week, whichever comes first. And if you want maximum security, you can use the prediction-resistant mode, in which you're calling our API at every call in order to reseed your RNG. So let's take a look at an example of integration into an existing cryptographic protocol. So for recall, what is threshold ecdsa? Instead of having one user that have a secret key and that generates a signature, we're splitting that private key into different shares, and then each user has a share that he used to generate a partial signature, and we can combine this partial signature to get the final signature. So it's a way to split the private key to have some more security. And we could say that it already provides enough security. Like if each user is generating randomness on its own, maybe I'm able to guess one part randomness, but it will be very hard to guess the other. But that's when we see that we have some setups in which it's difficult. For example, when we have some virtual machine and in some configuration, if they have some same setup configuration, we can end up by being able to gather randomness from all the VM concurrently. So here we're having the code of the Lockness repository from DFNS, in which they perform threshold ecdsa. So first we define our IPFS random source with a beacon key, and there we're able to call it like this with ctrng.ipfs, and we give our beacon key as an input. And once we've defined our ctrng, we are simply able to call it with ctrng.nextBlock. And so for each user, each party in the protocol, he's calling a block in the ctrng protocol, and we're having a base seed. And then this base seed can be used in different parts of the protocol, in the keygen, in auxiliary data generation, which is the key generation and splitting part, and then we can run signing. And so here, in this specific repository, they do not use our specific DRBG, so we tried to adapt to their implementation. They're using their seed, and then they are deriving it for each stage. For example, here it's key generation, so it's stage 1, and so for each stage, they derive their seed in order to get local randomness that is different for each round without having to retrigger different randomness generation. And yeah, so we derive randomness, and then we can run the keygen. And yes, that was the big picture. So thanks for being here, listening. And if you have any need for randomness integration or anything else, let me know.
Great. We are happy to take any questions from the audience, or we will be also here later on. I think we have still quite some time. Yeah.
Very technical deep dive, so thanks for that. I have a bit of a, I guess, general question. So there's been a destruction of a couple of SpaceX satellites in the last 2 days. I think 2 went down. Is there any data redundancies that you're thinking? Like if there's anything in space and you cannot service that and it goes offline, like you probably cannot store data for long periods of time there. So how did you lose that?
Yeah, it's a great question. Yeah, it's a great question. So we are actually on that part already thinking of the designs with respect to that. And it's kind of a layered approach. So one part, of course, if it's a single satellite that we'll be initially having, it's of course hard to have too much redundancy on that front of if something goes wrong with a particular spacecraft, it's a problem. But already on this particular spacecraft, we actually are adding multiple redundancies. So we, for example, have more of the same boards on board of the particular satellite as well. So in case one of the boards is, for example, damaged due to radiation or over the extended period of time of just being in a bit more of a hostile environment in space, we can switch to the other board. And also on the particular board, we actually have 2 instances of the TEs, so that way we can actually handle the particular sensitive compute in 2 different modes. And with respect to the data itself, we are, since most of the sensitive operation will be running inside of the TE, we are actually also encrypting them with the respective key, and we are later on storing the copies of the encrypted data in different locations on the satellite as well. So that way, even if there is a issue with a particular storage, for example, the SD card, we have a way on how to deal with it. And moving forward, we of course want to also have a redundancy across multiple satellites. That's also the motivation why we don't want to have only a single satellite, but a constellation, because you can later on distribute and synchronize the state across multiple peers and satellites in space, because what you're mentioning is possible, it can happen. And in general, also there will be a churn in the network. Like some satellites will disappear, some satellites will join. So you'll basically have to always make sure that there is enough redundancy across the different peers. One of the solutions Toufic was talking about is, of course, to use, also at least on the cryptographic level, to protect the private keys is to thresholdize them and have them stored at multiple locations, and think about it in a structured manner. We're actually currently like working on a more detailed blog post on outlining our strategy, which is like a mix of hardware and software solutions to make sure that, for example, we are on a regular basis also doing health checks, because even if the data are stored, it doesn't mean that they are healthy. They can, for example, be a bit flip on the radiation front. So we want to also have a regular checkups that basically all of the health of the files is still up there.
Right. Can I actually add to this? You said there's a bit flip with potential radiation, and I assume that with like solar flares, and it might happen more frequent than you might expect. So like, what kind of like health checks would you perform, and how do you verify that the data is still like the randomness is random, it's not like becoming unrandom in that sense?
For randomness, actually, this will maybe be helpful for us, but for example, for private keys, it can be a problem. So we want to be either doing checksums of the private keys if we happen to have access to them. This is one part. And if, for example, if they are generated and stored inside of the HSM, we cannot, of course, do a checksum on the private key because we never get to see it. But what we can do is to just make it sign a dummy data and verify it against the respective public key, basically. And if there will be some issue that we'll observe, we will have to regenerate the whole private key and the successive keys afterwards. So we will have to basically do again like a layered approach to solve this issue. But on a positive note, our satellites will be running on LEO. And actually, if you do quite a reasonable effort of putting some shielding onto the payload, you don't really have to worry about radiation as much. At least when talking with partners and discussing what is the likelihood of single radiation event happening. For example, the bit flip. During the experience of their spacecrafts, it never basically happened in the past. So in LEO, actually, you are quite safe because you are still quite close to the Earth, and it's not such a big problem. But of course, what is a general problem is that your hardware will be decaying a bit faster in comparison to on-Earth solutions as well. Yeah.
Hey, thanks for the talk. I have a question because I don't know anything about space computing. How are you going to deal with the outdated computers? For example, you send a computer today, in 10 years, the compute power that it has is not state-of-the-art anymore, and I don't want to use it, so how are you going to sort them off?
Yeah. It's a feature and a bug of space, in some way, but basically they will burn. So they will eventually burn on a re-entry to the atmosphere. So, which is, I think, we are using it currently more as a feature, because if you have sensitive key material that is generated in space and burns on re-entry, it's quite hard to actually go and try to get the private keys once the spacecraft is there. But definitely it's something that we have to think about, but at least as of now, especially if you are launching satellites into space, you also have to have so-called sustainability plan, which basically is kind of telling you what is going to happen with your satellites at the end of the life. For LEO, it's rather straightforward. They will likely just burn. For GEO satellites, it's quite funny, but they basically don't want to use enough propellant to be sending the satellite back to Earth and burning in the atmosphere. They just push it farther from the Earth and then just stuck there. So actually, if you look at some of the pictures, you basically have a graveyard of old satellites that are beyond the geostationary environment. So they are still there from 70s, 80s. They're just chilling there. So for us, we want to rather burn them in the atmosphere because we're focusing on LEO. Yeah. Okay, then if there are no further questions, well, feel free to reach out afterwards and hope to see you around. Thank you.